So I'm a part of the team at the University of Queensland, Australian Institute for Bioengineering and Nanotechnology, which works closely with Aboriginal partners on advancing nanocellulose technology. And so this technology spreads out of the Australian desert, quite literally, and we're working on a species of grass which is popularly called spinifex. It covers approximately a third of the Australian continent. It grows primarily in arid zones of Australia and is extremophile, which has developed properties to allow this grass to grow in extremely low rainfall and high temperature conditions. So there's a lot of this material that we can do something about, and the Aboriginal people have already found some interesting applications for this grass. So now we, in the time when we're looking at natural resources, we're looking at using this for advanced material. And so why we're actually looking at plant material is because plant material is built with this hierarchical structure from macro to nanoscale, and every plant consists of this complex hierarchical structure which contains cellulose, hemicellulose, and lignin. And in particular, cellulose is interesting when we look at the nanoscale. So nanocellulose fibers have got some very interesting properties, obviously the renewability and making it a sustainable resource. But nanocellulose, or CNF, has also a very high aspect ratio. It's strong, it's thermally stable, which makes it very interesting in a range of applications. So this is a couple of applications that we're looking at in our group. And we're looking to use these materials, nanocellulose, as fillers to make nanocomposite material. And obviously in applications like medical textiles, we use the high absorbency of cellulose and the ease of functionalization with different chemical moieties. And for example, in the packaging or the construction material industry, we're looking at adding strength to the material with trying to reduce the use of synthetic fillers or polymers. And so up until last year in my PhD, I was looking at a range of grades of the material that we can produce. And I should also mention that in our group, we have a pilot plant facility where we can produce this material at a kilogram scale. And so I looked at several different grades, and we could freeze dry this material, which looks like in the photo in the corner here. So freeze dried nanocellulose fibers. We understand quite well their properties. We understand their chemical their chemistries, their morphologies, their crystallinity. But what still was very difficult and challenging for us to understand was their mechanical properties. And this is particularly important in making nanocomposite materials, because in materials like synthetic nanofillers and nanofibers, it's easier to test the properties in electron beam. But unfortunately, with natural materials, it's challenging to measure the mechanical properties. They're not homogeneous. They're quite complex. And so we are trying to understand those grades that we produce, and we produce them by selectively removing different components like lignin, hemicellulose, and just leaving the cellulose in our material. And so here is where the AFM technique comes in place. It proves to be advantageous in testing mechanical properties of nanofibrillate cellulose. And this is for obvious reason. It doesn't degrade the material, it's non-destructive. And the new addition to the ANFF suite at UQ is this Bruker dimension icon AFM, which provides the opportunity to measure nanomechanical and nanoelectrical properties of materials simultaneously with the topography and roughness of the materials of interest. And to add to that, this instrument is equipped with a scan assist mode, which makes it quite relatively easy for the user to use and make the measurement, and especially for an AFM novice like myself, that is a big advantage. Sorry, just to go quickly, the measurement is performed in a tapping mode where the piezo controls the deflection of the cantilever, and then the instrument online produces the force curves from which the modulus is calculated. And so in this particular application, we were using a DMT model for calculation of the modulus, which I'm not going to go into details because I'm probably going to run out of time. But what's interesting is we looked at a couple of different grades of our nanocellulose, and we went from with the two of our most basic grades, where we use relatively low energy and chemical consumption into making those materials. And we were able to map those fibers deposited on a mica surface, and obviously we're able to also measure their mechanical properties. So we measured the DMT modulus, and this is still in progress, but so far we were able to analyze some bundle and single fibers to understand whether there's any differences, because we thought that perhaps the bundles could be either heterogeneous, have different composition, but we actually interestingly found out that the bundles and the single fibers have the same, show the same modulus, which is just below 2 gigapascal. And we looked at the indentation depth. So the indentation depth is obviously the same for both bundles and the single fibers, which also shows that, actually confirms the hypothesis that they're probably quite homogeneous on that scale that we're looking at. And then just, we looked at some commercial cellulose product, which is CNC, cellulose nanocrystal. Cellulose nanocrystal is a pure high-crystallinity material, and it's sold internationally as a nanofiller. And we were able to compare two of our different grades. So, and that black dot is a grade which contains both lignin, hemicellulose, and cellulose. And the gray triangle is where we remove lignin, which is thought to be a stiffening component of nanocellulose fibers. And we compared it to a pure CNC. And interestingly, we were able to see that both the CNC and the CNF with the removed lignin component have very similar modulus with just below 4 gigapascal. So that was very interesting, and it's a good result that we're going to go forward with to test different grades of our materials. And just to finish off, I would like to say that in this case, it's not the sky is the limit, it's the nanoscale that's the limit. So this technique is applicable to virtually any nanoscale materials. And we're also doing some collaborations with other groups at the University of Queensland, testing other nanomaterials like amyloid fibers and polymer nanoparticles, and trying to test their degradation behavior and predict their modulus before and after degradation for drug delivery systems. So this instrument available at ANFF here at UQ proves to be very advantageous and quite simple and easy to use for users, and offers a lot of, I guess, opportunities to test materials for various applications. So with that, I would like to give some special thanks, first of all, to our funding collaborator, Dugalungi Aboriginal Corporation, and a special thanks to Kinari and Jeff for their patience in training, and to my group leader. Thank you very much for your attention.
Thank you so much, Katarzyna. It's really nice to hear a bit more about the Spinifex work. Slido is very sad because there's, oh, actually the question has just come in. Awesome. From Elena. What is the diameter of the fiber? How did you calibrate the radius of the cantilever?
Yeah, so the diameter of the fiber ranges between a couple of nanometers, and we've seen as small as even 2 nanometers fibers up to, so this is for single fiber, they can be up to or down to 2 nanometers, generally about 5 or 7 nanometer in width. We are not able to determine the length just because they form a network when they're dry. And the second question was about the diameter of the cantilever. So we have been using 2 different methods. So one is a relative calibration method where we basically test, so this is a slide that I skipped. We use a calibration sample that has a known modulus, and we calibrate the modulus and adjust the radius of the probe. And another way that we've been testing, and I've actually done some comparison, and the results seem to be not significantly different with those 2 methods, where we use a sample that we can calibrate the radius of the cantilever itself. So Bruker actually provides this type of sample. So we calibrate it with that standard tip check sample, and we can find the diameter of, the radius of the.
Awesome, thank you. Thank you so much, Katarzyna. Just to remind you, everybody, of the Slido details. So the code for Slido is 808244. Don't be shy, put your questions on Slido, it's a lot of fun. Thank you, Katarzyna, once again for an awesome talk. Please join me in thanking her.